Hello and welcome. Today we're going to talk about the proof of the antiderivative theorem that we covered last video. So let's talk about that theorem again. Oops. So our theorem was, and we called that the antiderivative theorem, and then we say that if f of z is continuous on some domain D that's in the complex plane, then the statements A, B, and C are all true or none are true. Which is to say, another way of saying that all these statements are equivalent. Okay, the first statement is that f has an antiderivative f in D, and that means that f prime is equal to little f. Okay, so big F is what we call our antiderivative. Okay, the second statement is equivalent to the first statement, and that is that the integrals of the form f of z dz for contours that are completely inside our domain, from points z1 to z2 can be written as follows. F of z dz can be written as integral from z1 to z2 of f of z dz, and it has the value of the integral, of course, is just the antiderivative evaluated at the endpoints, the difference of the antiderivative evaluated at the endpoints, like so. And so that, of course, is the fundamental theorem of calculus, essentially, in the complex plane. And right here, this statement right here is just saying that it's independent of path. All right, so if I have a point z1, and it's all inside of D, our domain, and we have some contour here, c1, all the way to z2, but I could also go some other way. I can go this way on contour 2 and get the same way. So I can go on this route here or the other route. And either way will lead to the same result of the value of the integral, which is just the antiderivative evaluated, the difference of the antiderivative evaluated at 2 points. And finally, statement C is that closed contours C that are lying completely in our domain all integrate to 0. And what I mean by this is the integral of any closed contour is equal to 0. So what we're saying here then is that A is equivalent to B, so we can write it as a double implication there, and likewise with C. All right, so we saw that before. We saw some examples of how this works. So now let's see if we can just prove this theorem real quick. So the proof is fairly straightforward except for one part, and we're going to go over this. So the first thing we do is really what we have here is A implies B. We also have an A implies C, and vice versa. So what we're going to start with is just the first step will be to have this implication. A implies B. So we're going to start with the idea again here. So we're going to suppose that there exists some function, capital F, such that the derivative equals little f. Okay? So what we know about this, and so now we're going to take a contour, and we have our contour here, our contour which lies in D, and I want to compute the integral, right? So first of all, we have this integral, f of z, and we want to know how to compute this integral. And we know we have a constructive way of computing it. We have integral from, we'll call it we'll call it a to b, and this is for t. So what we have is a contour, z of t, which traces out our contour like so, and we have some point t equals a and t equals b. I should distinguish that. And that's our contour, and we're parameterizing it by z of t, and we know we can write it as f of z of t times z prime of t dt. Okay, so first of all, note, if I write it as follows, d dt of capital F of z is equal to f prime of z of t times z prime of t. And that's just the chain rule, right? But then we got this further piece here that capital F prime, of course, is little f. So what that means then is, if I go over here, is I can rewrite this as a to b. Wherever I see this, I can put this in its place, d dt of capital F of z of t dt. And of course, this is the fundamental theorem of calculus. This integral, of course, or this derivative here has real and complex parts, but the integral we can perform independently for each part, so it's just two real-valued integrals. But we can write it as follows. That's simply going to be f of z at the point b minus f of z at the point a. And of course, this point here, we're going to call that z1 to z2 in the complex plane. We can rewrite that as f at z2 minus f at z1. So that establishes this, this result here. And so that's true for any contour. So that could be contour 1, but that could be any contour. I could have done that to contour 2. It would have worked out the same, right? And so there's only one little asterisk here, is that z, we're assuming z of t is smooth, and that means z prime exists and is continuous. And clearly we want contours also that don't always, are maybe not always smooth. And all we have to do is sort of break it up into pieces and perform the same calculation on pieces, and there's nothing really terribly enlightening about that. Okay, so that proves the first implication, and now the second one. We want to prove that B implies C. Okay, so again, this one's pretty straightforward. So now we know that if I take a pathway, if I take a contour, I go like that from Z1 to Z2, and that's contour 1. Then I take another contour here, like that, and that's contour 2. Part B states that we're going to assume part B, assume B is true. And that statement means that integral of C1 f dz is equal to integral at C2 f dz. Okay? But we also have another, we know this is also true. We can write this as a negative C of negative C2. Negative C2, of course, is just going in the opposite direction, right? Okay, right, and we also know that if I say, if I take C as a closed contour, such that we can actually say that C is equal to C1 union minus C2, right? And so that would be the contour that goes like this, from Z1, and then it goes around like that, back to Z1. So it goes up to Z2 and then comes back. So it goes like that, and then it comes back, like so. All right, so we can write that then as, we can keep writing this then. So that means the integral of capital C, or of C dz is equal to the integral of C1. We can always break this contour integral into two pieces, plus integral minus C2 f dz. But we know that this right here is equal to, we can write it like this. Everywhere I see one of these, I can put this in its place. Or everywhere I see one of these, I can put that in its place. So I can write that as minus C2 f dz plus integral, sorry, that should be a minus C2 there, minus C2 f dz. Of course, we have a plus and a minus of the same things. That has to be 0. And so this is true for any closed contour, because I just said, so C is any contour in D. Therefore, B certainly implies C, which states that any closed contour integrates to 0, which is certainly true here. Okay, so now let's kind of do a recap here. What we have is we started with A, and we proved B. We went to this way, and then we went this way. Okay, so by transitivity, I've proved A implies B, and then B implies C. Therefore, I've implicitly already proven that A implies C. So what's left to do now is to go backwards. We need to go this way, and then we need to go back that way. So that's the only task we have left. Okay, so now let's go to the next page. So we want to prove that C implies B. Again, I'll put that up there. We have A. We've had that implication, and we had that implication. So now we just need to go back. Okay, to fill in that one, and that's really simple. In fact, we essentially already done it. If I have a contour as follows, like that, and that's a closed contour, and it's equal to 0. So that is the statement of C, that all closed contours integrate to 0. I can always, of course, break it up into two pieces, call it C1. And so if I want to take an integral involving an integral from Z1 to Z2, and that's, of course, the domain of, that's germane to the B's implication about antiderivatives, I can always write this as follows. So I can always write this as follows. Sorry, I'm getting a little behind myself here. I can always write this as C1, and that's C2. And that is f dz plus integral C2 f dz. Okay, and then of course I know that is that integral f dz, and that implies then that C1 is equal to integral negative C2 f dz. Okay, and that says, this basically, that proves independence of path Okay, but we're not quite there yet because we haven't, and that's the essence of what we're doing here. But we haven't proven that we have this, that we haven't proven that there is this antiderivative. Okay, so we're not quite done with that. So we actually, what we need to do is try to prove this one here. So let's see if we can rewind there for a second. All right, so let's prove C implies A, right? And this, of course, is that all closed paths go to 0. And this is, of course, that there exists an antiderivative such that f prime is equal to little f. Okay, let's see if we can do that. And so, in order to do that, we need to we need to define this. We're going to define capital F of z is equal to this thing, starting at z0, where z0 is just any arbitrary point in our domain, and going to z of f of z dz. Okay, again, I'm going to put this in an asterisk that we don't know if f prime equals little f. In fact, we don't know this is even differentiable. Okay, so we want to actually prove that. So what we want to do then is we want to take its derivative. So we need to take the derivative of this, so we're going to actually do that. So we're going to take f of z plus delta z, some small perturbation, subtract it from z itself, f of z itself, and divide by delta z. Okay, so we can write that as follows. That's going to be 1 over delta z times integral z0 to z f dz. Oh, I should have put an s in there as a dummy variable. I'm sorry. Let's put an s in there, ds. All right, and then minus integral, and that should be s or z plus delta z, and z0 to z of f of s ds. Okay, all right. So first of all, what we can see then, if z0 is some point here, and I'm going up to z plus delta z. Likewise, and if I have another point out here at z, right there, so this represents that integral there, integral this way, on that contour, and this one this way. Okay, but now I'm taking the subtraction of that, so that's the same as going the opposite direction, right? In which case, because we have independence of path, we can go directly there. So we can write this as delta z integral from z to z plus delta z, okay, of f of s ds. Okay, so that looks pretty good. So now the next thing we want to do then is play a little trick here. So we have that expression. Now we want to prove this is close to f of z, right? Because this is effectively right here f prime, right? As delta z goes to 0, this is going to get close to f prime, provided it exists. All right, so we need to prove that f prime gets close to this. So what we really want to do is subtract these two things and say that they're zeros. So we want to prove that 1 over delta z, integral from z to z plus delta z, f of s ds, minus f of z. We want to prove this whole thing here goes to 0 as delta z goes to 0. Okay? All right, so let's see if we can do that. So again, I'm going to write that up again here. We have f z plus delta z minus f of z all over delta z. We say that that was equal to 1 over delta z, z to z plus delta z of f of s ds. All right, and now I want to I'm going to, give myself a little bit more room. I'm going to subtract that from f of z. I'm going to subtract f of z to both sides. And now what I want to do then, though, so I want to prove this goes to 0. What I'm going to do then is rewrite f of z in a slightly clever way. Okay, so what I'm going to do then is I'm going to multiply by 1 over delta z. Then I'm going to assume that our contour from z to z plus delta z is just a straight line. In which case, its arc length is going to be simply, or the integrated value is going to be delta z, right? So we can write that as this, as z to z plus delta z of ds. Okay, and what we're really saying here is this thing right here is equal to delta z. Okay, I'm going to rewrite this a bit more, and that becomes 1 over delta z, right? Integral z to z plus delta z, f of z ds. Notice that there's a z there and an s there. So this is simply, in the eyes of the integral, this is a constant. Okay, so now with that, I'm going to go back up to my line up there and go down again here. I'm going to make that equal right there. I'm going to have 1 over delta z. We can factor that out. We have an integral z to z plus delta z. And I see I have an f of s in there. And then wherever I see this, I can, of course, put that in its place. So we get a minus f of z ds. All right, so those are equivalent expressions after you just do a little bit of simplification there. So I want to prove that this thing goes to 0. So, of course, the thing I can do is actually put absolute values on that. Because, of course, if the modulus goes to 0, the thing inside is also going to 0. Right? So I'm put an absolute value on that. Then we're going to use our bounding modulus for integrals. Of course, that becomes 1 over z modulus, integral from z to z plus delta z of the of the integrand, the modulus of the integrand, ds. Okay, so recall that the only assumption we had on f is that f is continuous. Okay, and that implies then that for every epsilon greater than 0, there exists a delta such that when s minus z is less than delta, it implies then that f of s minus f of z is less than epsilon. Okay, so of course we know that s minus z is actually less than or equal to delta z, right? Because we know we're starting at z and we're going to z plus delta z along this integral here, okay? And so s, of course, is some point. S can be it can range along this whole line here. So it's got its maximum modulus has to be it has to be smaller than delta z, the modulus of delta z. So we can take that to be our delta that guarantees this epsilon. Okay, I don't have to actually find it because I don't know what f is, but we know that f is continuous, so we can always find this. All right, and that means I can write this as follows. I can take this expression here and write it as follows. That's greater than, strictly greater than 1 over delta z modulus of integral of z plus delta z of epsilon ds, right? So this I can just replace with this epsilon. Of course, epsilon is a constant with respect to this integral, so I can write that as epsilon over modulus of delta z. And we have this here, z plus delta z ds. Of course, this thing right there is exactly delta, is exactly delta z. I should actually just I should have put this in so when I did this, I needed to actually still put absolute values on or a modulus on the outside of that thing. So this thing becomes just the modulus of delta z, in which case we have epsilon. And that means, of course, as epsilon can go arbitrarily small, it implies then that f prime does in fact equal f, because that means this whole thing goes to 0. Okay? So that is the proof of that theorem. And so what we have then is that C implies A. Okay. So if I have A implies B implies C, And we have that, and then we have then that we can go around that way as well. Okay, and we've also proven that. So we've also proven then we can also, so we can get anywhere from any point on this thing. So we could have gone that way, but as long as I know A is true, B is true, B is true, then C is true, and then C is true as A is true, that means that also that has to go in the opposite directions as well, as follows. Of course, we also proved that that was true earlier. So all of them are true, and we have proved our theorem fully. All right, so that seems to have it all worked out. I hope you enjoyed that rather long proof.